business development at Innovator. After a hiatus of 2 years, we're glad to see you this morning. Thank you very much for being here. To hear, and actually we'll have a very good presentation for you with regarding skin barrier dysfunction, atopic dermatitis, and beyond. Since we last saw each other at AAD 2019, Innovator has grown significantly. Here's a quick view at where we stand at Innovator in 2019. Our CRO operations, focused in dermatology, has now managed over 110 clinical trials in the last 8 years. Our clinical research unit has been involved in 440 dermatology clinical trials. Our network of dermatology research sites has grown to over 2,600 sites in North America and in Europe. And finally, on that slide, our 350 employees are located in Canada, US, Europe, and even in Asia, enabling us to manage international trials. Here you can see how our the 110 studies I just mentioned to you are separated by phase. 57% of these studies we manage involve a systemic drug. And we have recruited overall close to 10,000 dermatology subjects. In conclusion, Innovative Research is a clinical CRO focused in dermatology, offering A to Z service that often starts with writing a scientifically sound study protocol. Our expertise with topical compounds involves multiple design, like max use studies, and the use of alternative means to define mechanism of action of topical drug, like the use of tape stripping. We also work very often with systemic compounds, as I just mentioned, in SAD and MAD studies, for example, combining healthy volunteers and specific indication subjects to assess preliminary efficacy signals. Enough of me. If you have any questions, please, after the call, after the talk, come and see us and we'll certainly answer your questions. But you are here today to hear about our two speakers and their talk. I would like to invite my colleague, Anna Palijim, who is the Associate Director of Early Phase Development at Innovator, to come and present our speakers. Anna?
Good morning, everyone. Thank you for joining us. I'm pleased to be presenting our two panelists today that are key leaders in dermatology research and have a combined publication of over 500 scientific articles. Dr. Alan Irvine joined us from Ireland. He is a professor of dermatology at Trinity College. He's also the founding president of the Irish Skin Foundation and the International Eczema Council. His research focuses on molecular genetics of skin disease, including rare skin disorders. Dr. Robert Bissonnette is the president and founder of Innovator Research. He has conducted and consulted on hundreds of trials and is a principal investigator on multiple investigator-initiated studies to further our knowledge and understanding of skin disease by applying molecular novel techniques. Today, they will be discussing how the disruption of skin barrier plays a role in atopic dermatitis and methods to assess skin barrier integrity in clinical trials. Dr. Irvine, I invite you.
Merci Robert pour votre très gentille invitation ce matin. C'est mon plaisir d'être avec vous ce jour. And now in English, en anglais, on y va en anglais. So we are going to talk a little bit about some things that I thought might be interesting to share with you about atopic dermatitis and skin barrier. It's a complex subject. We've got 25 minutes. Audrey's sweating on my time. I'll get through it or not, but I think we will. And we'll have a bit of fun talking about some different things, some different mechanisms, and I think think Robert's going to talk a lot about clinical trial setting. It's a real pleasure to be with you and see this impressive body of work you've done, and congratulations to all of you, and of course Robert as the head of all of that. These are my disclosures. First thing I want to say is that atopic dermatitis, it's a complex and interacting pathogenesis. We have skin barrier dysfunction, we have immune dysregulation and dysbiosis, and of these, we're beginning to understand all of them in much more depth, but importantly how they interplay, and then we're beginning to understand how we can switch some of them off. And I'm going to come back to this theme again and again, because the things that you've studied in your trials, they've mostly been immunologically active molecules, and that's because the immune system is much easier to target, it's much more tractable, druggable than repairing the skin barrier or improving dysbiosis. But we'll talk a little bit about how these things interact. Very brief bit about epidemiology. Atopic derm is increasing in countries that are becoming more urbanized, that are changing from urban to rural environments, and a lot of that is through pressure on the skin barrier, and we're beginning to understand some of those, that kind of completeness of exposure, so-called the exposome, everything that you're exposed to from conception in utero through to death, all of the environmental exposures contribute to driving skin barrier dysfunction and atopic dermatitis. And you can look at some of these that are beginning to become understood, why when you move into cities, atopic dermatitis becomes commoner, and that can happen in China, in South Africa, in South America. We're seeing lots more atopic dermatitis in these rapidly industrializing and urbanizing countries. And there are lots of toxic environmental exposures when you move into a city, everything from tobacco smoke, but diesel fumes, diesel microparticles, all of which can either through epigenetic manifestations or direct pressure on the skin barrier, which is the subject of today. We can damage the stratum corneum, damage lipids. We can drive through the AHR receptor, and again, that's a druggable receptor which is in clinical trials, and you may have worked on some of those molecules. The AHR is a xenobiotic receptor that regulates skin barrier function and differentiation, and we'll come back to that in the talk because it's a druggable target and because it links in the barrier, the microbiome, and the environment. And all of these can amplify stressors on the skin barrier and break it down. So one of the things I studied about 15 years ago was filaggrin. That's a big green molecule out here, stained green in the stratum corneum. It's about 70% of the dry weight of the stratum corneum. I'm not sure my printer will reach, or my pointer will reach across there. Maybe it will. Oh, it will, yeah. So this is filaggrin. These are the basal keratinocytes here, and you can see it's just a huge molecular presence in the outer aspect of the skin. And you can imagine this area has to respond to every environmental change. It's our first barrier, that kind of final differentiated barrier, the stratum corneum. So if you go from a dry environment to a wet environment, it has to adapt. If you go from in utero to ex utero, obviously you only do that once in your life, but it's a huge shock, you know. But it's an incredible change. If you go from a sunny climate to a dry climate, if you go from indoors to outdoors, this has to react, and you get seasonality and changes in seasons with this, and it's just something I want you to bear in mind. This is our sensing and our interacting with the environment is through this really fascinating organelle called the stratum corneum. If things go wrong in this, the consequences are pretty dire. There's a paper in the New England that we did a number of years ago. If you have a mutation in filaggrin, and mutations are all big, gross loss of function mutations that knock out the function of one or both alleles, so you lose 50% or 100% of production. You have a very high incidence of peanut allergy, for example, like it's a 5x for peanut allergy. It's about a 3.5x for atopic derm. It's about a 1.5x overall for asthma, but importantly, only when you initially have atopic derm. And this is work that we worked out over 15 years ago, and it still stays true today. So having a big molecular problem with your skin barrier has consequences for atopic and allergic diseases through the entire lifetime of the child or adult who has that. You know, there's very few single gene mutations that cause that degree of burden of disease. And remember, in the region of about 8 to 10% of people in most populations outside of Africa, so Black Africans, Sub-Saharan Africans, don't have many filaggrin mutations, but they're there in Asia, in South Asia, in South America, in North America, in Europe. They're there in many populations worldwide, and they cause billions of people morbidity. So remember, atopic derm has got its origins in early childhood. I mentioned the big environmental changes that we have. Oh, the timer's not on here, but yeah, I'll just keep going. We'll be fine. Yeah, be fine. We'll be good. So just some of the work that we did, just looked at infants' cheeks, for example, and we looked, why do kids get eczema on their atopic derm on their face in their first year of life? And this is years of work. Again, I was just talking to Anna earlier about non-invasive skin testing. We did this in newborn and neonates, and we did it right up to 4 years, and we in different cohorts. Easily done, and we could look at things like natural moisturizing factors. So filaggrin contributes about 70% of NMF, but you can do this on a tape strip and HPLC it very easily and get really good reproducible results. So the cheeks are very low NMF, and it's very delayed to mature. You don't get to maturity until about 3 years, as opposed to everywhere else, which is matures very rapidly. There's probably some evolutionary reason for that, maybe to do with mother's breast milk or transfer of antibodies. There's different theories. There's low cohesion, so it strips off super easily, and the corneocytes are really immature. So this is an area where if you put food protein on the cheek as opposed to in the mouth, food is meant to be eaten, not spread on the face. But of course, young babies are not precise feeders. But this is a real window of entry for initiation of atopic derm and for allergy. So if you're rubbing peanut on the cheeks, not that you would do that deliberately, but a big study in Bristol looked at, for example, nipple balm for nursing mothers. The moms who used peanut-containing nursing balm, there's a huge increase in risk of peanut allergy in their offspring. And so we know that as a result of the LEAP study and other studies, that feeding orally really leads to tolerance, and feeding or exposing antigens, including food proteins, through the skin leads to allergy. And that's just the way our type 2 immunity is set up. We have type 2 immunity to reject parasites, and it's very closely linked, of course, with the neuroimmune axis. So if you get a parasite, it drives an itch. If it's in your nose, you'll sneeze it. If it's in the lungs, cough it, vomit it if it's in the gut. And if it's on the skin, you'll scratch it to get quick removal of parasites. That's where our Th2 immunity exists, and I'll show you later in the talk. It links very tightly with the immune system, so you get rapid responses, but you're not supposed to have it switched on all your life, as in atopic derm. So what about when you go from the aqueous environment into the arid environment? This is really birth from the completely or almost completely xenobiotic, completely sterile environment of the womb. And we know the womb is not entirely sterile now with microbiome studies, but it mostly into the arid environment. Well, what happens there is filaggrin starts to very rapidly get broken down. So the skin senses that it's no longer in an aqueous environment, and it burns up filaggrin to produce NMF. So this is like a store, it's like something in reserve for prenatally. It's built up, and of course babies who get born premature don't make this transition so easily. But for term babies, these are all term babies where we looked, and within the first 24 hours, suddenly you start to chop up. We sense in some way that we're now in a dry environment, we chop up filaggrin. And we do this seasonally as well, although in a much less dramatic way if you move from a dry environment to a humid environment. And that's why people's skin, well, one of the reasons why people's skin gets worse in the winter, atopic derm and so on. And it's an important thing with seasonality, but the biggest and most violent change is pre and postnatal. So again, just to come back to when the baby's born, all of these influences that she or he may be exposed to. One of the interesting receptors then, of course, is the AHR receptor, and it's a complex receptor. AHR, you know it's in the dioxin pathway as well, so it's involved, it's a real central player in skin barrier maturity. And I'll just see if I can identify it over here for you. So coal tar, for example, inhibits this, and it has positive pressures on it, but pollution can have different pressures on it. And this is where some companies are obviously drugging the AHR receptor. I'm going to show you a little bit where the microbiome comes in as well. This is work by Juice Schwalik years ago in the JCI, just showing that external pressures like tar could actually drive filaggrin to increase in its strength, and also it's influenced by the by type 2 immunity. Water hardness also linked to atopic derm, and good data from England looking at this. and a strong interaction, odds ratios of about 28%. But when you break it out and you look at people who have filaggrin mutations and who do not have filaggrin mutations, all of that difference is the interplay between hard water, calcium carbonate rich environment, and filaggrin mutation. So a weaker barrier, it doesn't have the reserve, it can't have that filaggrin that can chop down and adapt to its environment. And therefore people who have that genetic defect will just show you the odds note here, will have a very high incidence of atopic derm. And there are studies now looking at putting in water softeners for people who have filaggrin mutations or whose families have filaggrin mutations. See, does that prevent atopic derm in England? It's a very expensive intervention to make, and you can't drink the water. So it's not a simple intervention, but it's an example of how the environment interacts with the skin barrier in different areas and how we're learning about that. Other things that we see are sites of predilection. This is a Danish study, Hans Bisgaard and his colleagues, and the red areas are where you get a lot of atopic derm in filaggrin carriers. And guess what? It's the areas that interact with the environment. So you're dealing with people who have less of a reserve, who have less of a threshold to interact with their outside world, and that's why they get it in their cheeks and they get it in their arms and hands predominantly. So there's significant interactions between filaggrin mutations and environmental exposures on the skin barrier, which I've showed you. And there's other things we haven't mentioned, like older siblings and phthalate exposures and things. There's lots of different gene environment exposures worked out now. I'm going to pivot a little bit to the microbiome. This is Staph aureus. This is Staph aureus, which doesn't sit like little eggs on the surface of the skin, but it's a man spreader. It spreads out and it takes all of the free seats in the carriage, with this thing called a micro or a biofilm. So it spreads everywhere on the skin, and it's a really critical bacterium, a critical genus and species in atopic derm. We know that more than 70% of people will be colonized. If you have it heavily colonized, it's worse barrier function, and it even inhibits responses to things like cyclosporin. We know from Heidi Kong's work that before you get a flare in atopic derm, these pink bars on this histogram are Staph aureus species, and you get a hegemony, or in other words, the Staph aureus begins to eliminate all of the other biodiversity of communities of microbes prior to a big flare. And then when you get a flare, it's pretty much the dominant pathogen, and then you get treatment and it recovers, and you get some degree of diversity of microbiome colonies afterwards. So having a hegemony of staph is really bad. It tends to flare the skin, and the question that we asked then is, again with Heidi Kong, which comes first? Does the dysbiosis or atopic derm? And these are difficult things, chicken and egg questions to work out, same as the skin barrier. And the answers are complex, but we have shown that Staphylococcus actually are protective against atopic derm. So if you've got lots of colonization with non-staph Staphylococci, you tend to have less atopic derm. And then others, Daniel Ho and others have shown that if you've got Staph aureus, it precedes getting atopic derm. So Staph aureus is a big player here, and it's uniquely adapted to human smooth skin. One of the things, it can adhere really easily, it can destroy the barrier, and it can drive inflammation. To show you how it does it, has all of these mechanisms, different clumping factors that are designed that perfectly hook in to our skin and our corneocyte surface, and really make it incredibly difficult to eliminate as a pathogen or as a driver. This is what normal stratum corneum looks like on scanning electron microscopes. Looks really quite neat and very beautiful. If you have filaggrin mutations, you produce these, I don't know if anyone remembers these when they were kids, stickle bricks. It produces stuff a little like this. So this is work that we did. This is atomic force microscopy. So you take here, you put a single live Staphylococcus on the edge of a little cantilever, and you rub it across and see where it adheres, and you look at these micro forces between the live staph and the surface of the stratum corneum in a corneocyte. So this is someone who doesn't have filaggrin mutation, and this is someone who does. And essentially it's just like stickle bricks. Staph just sticks to all these little pimples that get exposed in the stratum corneum. So it's incredibly adherent and very difficult to eliminate with topical or systemic antibiotics fully, other than just in a very temporary way. It's also developed various toxins like alpha toxin and proteases. It can hijack our own proteases by driving them once it gets into the stratum corneum, and it has its own intrinsic proteases that chop up like scissors, chop through the proteins of the stratum corneum, and it has alpha toxin, which is really elegant. This alpha toxin destroys tight junctions, it just bursts everything open, and it's really quite beautiful. It's a pore forming toxin, so it comes out as a protein from the staph. It's a secreted protein on the surface of the cornea side. It forms into a perfect circle and drills through the stratum corneum. So it's an extraordinary bit of evolution, an extraordinary bit of biology, and Staph aureus is just incredibly adapted to our skin, and is specifically on Staph aureus. Superantigen theory's been around for about 20 years, and many others, protein A, phenol-specific modulins, and others that directly drive inflammation. Staph loves inflamed skin because it can penetrate more deeply in through the stratum corneum, it can get into the dermis, and you can see once it's in the deep epidermis and in the dermis, it's almost impossible to eliminate. And some of these are driven through the TNF receptor as well. So all of these Staph aureus activities, they're enhanced if you have a filaggrin deficient epidermis, and they're enhanced with type 2 cytokines. So again, type 2 immune system's only meant to be an on-off, get rid of the parasite and move on with your life. It's not meant to be on for 20 years or 10 years or 50 years. So when it's there, it dissolves directly the skin barrier. And one thing I did want to mention just as a final microbiome piece, and this is Elizabeth Grice from Philadelphia, UPenn, just published this last year. Really elegant work looking at the commensals, so the healthy microbiome. And the healthy microbiome also works, remember I mentioned AHR, aryl hydrocarbon receptor, it also works through that to maintain the barrier. The same way as coal tar works, and the same way as pollutants, if they drive it in a U-shaped curve, can make things worse. So our normal microbiome is really important in maintaining the skin barrier and lessening inflammation. What about immune dysregulation? Well, we all know about that, the type 2 and all of the relevant cells and the key cytokines and targets. You're studying these all of the time. I know we have Almirall here who've got their IL-13 and other companies who are working on this. How does this interplay? Well, a stress barrier releases alarmins, TSLP, and many others that will cause type 2, IL-33s and IL-25, the other two, will cause type 2 polarization, and you get into a vicious loop with amplification in the skin. And the important thing is with atopic derm, the inflammation is in the skin. The peripheral signal is less important. It's a skin disease, and the peripheral signals are generally just leaching out of cytokines and cells that are in the skin that you pick up through a glass darkly, if you like, in the peripheral blood signal, but it's really a skin disease, and you get massive amplification of this when the alarms go off. And what does that do? It amplifies the whole circuit in a vicious cycle, breaking down more filaggrin and more skin barrier defects and driving more inflammation. The key cytokines we know are 13 and 4, and they signal through JAK-STAT, and you've been studying these in your molecules. Remember, there's a second barrier too, the stratum granulosum 1 and 2, and that's a barrier that's an antigen barrier. Normally, these dendritic cells, you see them reaching up in the stress barrier. So you've got all these type 2 alarmins dissolving the barrier, allowing the dendritic cells to reach up and sense what's out there, and becoming allergic sensitization through that. A bit like E.T. with his finger, here he is. Just that kind of, that's the E.T. finger there. And so what you're seeing is an active barrier, Langerhans cells and other immunoactive dendritic cells in the dermis and epidermis, certainly in the epidermis, will drive immune activation and long-term memory of allergies. And remember the Brian Kim's work, which came in serendipitously after all these molecules were in trial and some were even approved. But what he showed was really elegant, this neuroimmune axis that 13 and 4 and 31 and others signal through the dorsal root ganglia, through the JAK-STAT pathway, and it comes back and it makes perfect sense, that pathogen or parasite elimination piece. So you have a very complex, and I'm not going to go through this in detail, I can share the paper, it's one of our papers, just looking at non-lesional skin and all the pre-clinical abnormalities, the lesional stage through to the chronic lesional stage in atopic derm, and all of these are driving each other more actively. So of course, the only one that can really be targeted, we've spent years trying to correct filaggrin deficiency, it's gene therapy, it's incredibly difficult. We've got read-through with aminoglycosides and other molecules that caused read-through stop codons, but they were too toxic to use. And really the microbiome piece I'm going to show you briefly, but the only thing that you can really target currently in the clinic is the immune axis. But fortunately, when you do target the immune axis, you do begin to improve both the barrier function and the dysbiosis, and lots of companies have shown that now. Dupilumab, lebrikizumab, or tralokinumab have shown that both barrier and dysbiosis improve. I'm going to show you a little bit of data, just simple stuff, topical corticosteroids. This is work from our own lab, one of my PhD students who looked at infants who had under a year, who had 6 weeks of topical corticosteroids, and we looked at all their barrier function after that, and we also looked at their systemic cytokines, which was interesting. And what you can see here is transepidermal water loss, which you measure, and it was mentioned in your opening slide. That obviously improves, but the skin barrier function, the natural moisturizing factor, really doesn't. It goes everywhere. You don't fix the genetics by removing the inflammation, but you do allow the skin to repair itself, like a house that's on fire. Once you put the fire out, it can improve things somewhat with the chewable. What you will see in innate type 2 and even angiogenesis biomarkers, they all reduce in the stratum corneum with topical corticosteroids. But what you see, interestingly, is plasma biomarkers also reduce quite dramatically. And what we conclude from that is that either there's a systemic effect of the topical corticosteroids, we think is unlikely for 6 weeks, but we conclude is that the cytokines are really leaching out of the skin into the peripheral blood, and that fits, because it's a skin disease. You can also, this is not our work, but it's another paper just looking at the effects of normalization of the microbiome. You can, after topical corticosteroids, and essentially get a lot less staph aureus when you treat with topical corticosteroids. So remember the 3 axes, target the immune one, and you begin to correct some of the barrier abnormalities like chewable, and you begin to also correct the microbiome dysbiosis. We know how dupilumab works, you're targeting the IL-4, IL-13 cognate receptor. And this is Emma Gutman's work, just looking at duration of treatment and normalization of skin morphology, really, skin barrier morphology, and some immunohistochemical work on expression of skin differentiation markers. So again, if you switch off that type 2 signal, you get the barrier is allowed to restore itself. Put the fire out, and the house begins to repair itself. So can barrier protection prevent AD? Kind of holy grail, big meta-analysis, and long story short, this is the forest plot signal. It hasn't been shown so far. If you take babies who are at high risk of atopic derm, some studies show a lower odds ratio. The bigger studies do not, and they count more in the meta-analysis. Obviously, they're weighted heavier. So this has not been proven, and there have been 2 big studies, Prevent et al. And the BEEP study, one was done in Scandinavia, one done in the United Kingdom, and they got a negative result. And in fact, some of the heavily moisturized kids got more food allergies in both studies. So that's got some ways to go with technical. We probably need more advanced moisturizer, or perhaps it's never going to work. We need to see. We've some interesting data on ceramide-based barrier repair. So the results and implications are you can't really recommend population level interventions around moisturizing yet to prevent atopic derm. Finally, I talked about how complex the microbiome was to fix. This is the salivary tail, Rosie Uma's tail. Really interesting phase 1 in JCI Insight, beautiful paper, created a huge buzz, and the phase 2 read, I don't know if you did this in Novoderm, did you? I'm not sure. The phase 2 read out in September of last year. I had a call from a venture capital company in Wall Street a week before they read out. I had nothing to do with the study and no access to the data, and they wanted to know should they invest in this company or not a week before the type 2. I spent an hour saying I have no idea, because it's just a gamble. But yeah, it didn't work. It didn't work. They didn't meet primary endpoint. And I think the microbiome, as I've shown you there with Elizabeth Grice's work, and we understand so little of the microbiome and its enormous complexity that really difficult to make simple interventions and hope that that's going to have a profound effect size on this really very complex disease. But maybe we'll get there, and it might even be the gut microbiome that turns out to be more important, because there's a whole body of work around the gut and skin which we don't have time to go into. So some conclusions. Barrier dysfunction it's a cardinal feature. It's driven by genetics, the exposome in its full glory from conception onwards, and the microbiome, hugely important in positive and negative ways, with the commensals and the staph signal. It's modified by topical drugs and by systemic therapy, as I've shown some little highlights. Microbiome manipulation is hugely complex, and I think there's a lot to do there, and I think we will see that in the future, but it's a way off. Barrier repair is really poorly understood. You know, the effects of putting moisturizers on the skin, how that interferes with the terminal differentiation program of occlusion. You remember, go back to the birth, before and after birth, and all of those rapid changes. Really difficult to understand and manipulate that. These are people I've worked with that have funded me for the last 15 years, and these are the guys we're doing it for, so they don't. So thank you very much. Are we going to do questions after, Robert? Yeah. For now. We can do questions now.
Yeah, we can do questions now.
Yeah.
That's the most important presentation. Mine will be after, it will be a short one, but I think I want everybody in the room to have a chance to ask questions.
Anna, yeah.
Yes, I have a question. Thank you so much for a really interesting talk. I was wondering, did you look at the impact of microbiome on recovery, skin barrier recovery?
No, that's not been looked at. You know, those kind of studies where you do tape strips and look at chew well and see. I'm not aware of anybody having a look at that at all. A complex study to do, but it would be interesting. Hey.
Yeah, I have a question. You talked about filgrastim being modified in some patients. Have you looked at microbiome and the way that interacts with the pores that you're saying that stick out? Does the microbiome kind of attract?
Oh yeah, we do. Yeah, staph. Those are cornea desmosine probes. So we've done immunogold, and we know exactly what the even the piece of the cornea desmosine is, and we know exactly what the binding protein of staph is. We've done a lot of work with atomic force microscopy on that. We can even measure the forces, because you can put these little cantilevers on, it's like nanotechnology, and remove them and see what the pressure is before the staph will let go of the skin. It's fascinating. But that Staph aureus is the only one that seems to have that mechanism, clumping factor B, that does that. So it's got a kind of like it's got a dock and lock mechanism, right down to the molecular level. It locks in, and it's really hard to get off. So because it's evolved with us.
It's particularly Staph.
Yeah, particularly
Okay.
Staph aureus. Not even just Staph aureus.
Okay.
Yeah, we're all good. Okay, thank you for your attention. Oh yeah, go one more. Yeah.
Alan, do you consider the microbiome to be separate from their function, or is part of it?
The microbiome it's 100% part of it, and that's like Elizabeth Grice's work is some of the more elegant work that just came out last year, looking at the commensal bacteria, because everybody's been focused, from Heidi Kong's work, which is also beautiful, but looking at pathogens and damage. But what she was interested in was looking at homeostatic and repair mechanisms. And there's a real danger of crudely manipulating the microbiome and actually wiping out lots of, if you want to crudely say, the good microbiomes who are there maintaining in their microbial communities, actually putting pressure on the aryl hydrocarbon receptor, essentially working like a topical AHRX to intrinsically do that. So they're completely linked. And then once you rip the barrier up and you pour, when you rip the barrier, you're just flooded with type 2 cytokines, and that becomes a glorious environment for Staph aureus to go on. It links to fibronectin, so anytime you scratch and there's a little bit of blood and fibronectin at its end, it's just so good at doing that. So the commensal bacteria, the normal microbiome, is really poorly understood and really important. Yep. Oh yeah.
Just one more. You emphasized throughout the talk that the immune response is happening in the skin, that it is a skin inflammation. And we also see a lot of immune treatments that are systemic treatments and discussion of the gut microbiome with sort of an overall, maybe amplified immune state. Can you say a bit more about how those concepts interact with each other?
Yeah, well, they do. So I think one of the things that we've learned in the last 5-10 years is tissue-specific inflammation is incredibly important, whether it's the lungs, the gut, the nasal mucosa, even the heart and the brain. You know, they all have very tissue-specific immune mechanisms, immune activation. But of course, you can't. The only way to target those is systemically with small molecules or biologics that cross into those compartments, whichever they are. So you essentially have to drug the entire body to get to the tissue that's super inflamed, because we don't have smart drugs yet that only will locate to skin, for example. And sometimes that's a big benefit too. For example, if you're targeting 13 or 4 and 13, you're often dealing with atopic comorbidity. So people have very similar inflammation in their lungs and in their nasal sinuses or in their esophagus. So it can be really beneficial to do that. And other times you get off-target effects that you don't really want if you're using a JAK inhibitor and you really only want to target the skin. You have to take the off-target hit. Now the bit with the microbiome, I don't want to take too much time, but the bit about the gut microbiome that's really interesting is that I'm going to wind it up. Audrey's giving me the wind it up thing. So I'll talk to you offline about that to respect Audrey's dancing. Yeah, that works in English as well.
Thank you very much, Alan, for this very thorough and elegant presentation. So mine will be a short presentation on how to measure skin barrier integrity in clinical research. We've heard of the importance of the barrier. How can we measure this in clinical research? Skip that one. So there are many ways, many direct ways and indirect ways to measure the barrier. There are physical ways. We can look at gene expression, lipid content, and imaging. Today, I will focus on transepidermal water loss, gene expression, and lipid content, which are usually the ways that we can use in a clinical trial, specifically in a multi-center study. So transepidermal water loss is a natural phenomenon. So we all lose water through our skin. That's it. There's a typo about the number of ml per day. The increase suggests a skin barrier alteration. We can measure this on normal skin, and if it's increased, there's an effect on the barrier. What can increase transepidermal water loss? Mechanical destruction, obviously, of stratum corneum, cut, abrasion, friction. When we do tape stripping, for example, we have an increase in transepidermal water loss. A skin disease causing inflammation like atopic dermatitis, skin disease that would decrease lipid production, dry skin, xerosis, or mutations in one of the genes that are coding for proteins involved in the barrier. Now, we can measure this with devices. So transepidermal water loss can be measured. There are 3 types of devices that can be used to do this: open chamber devices, semi-open chamber devices, or closed chamber devices. So the easiest, simplest way of measuring this, and I would say the cheapest, is to use an open chamber device. This is how I started to use transepidermal water loss measurements in research many, many years ago. It was almost 20 years ago now, mostly in studies looking at treating dry skin. The cosmetic industry used these a lot. The way it works is that you put the device, you put the device at the surface of the skin, and then water is evaporated from the surface of the skin, and you measure the gradient. The issue with this is it's very dependent on what happens to ambient air, because it's an open chamber. And I remember when I used this for the first time in clinical research, I was getting very, very beautiful data for some patients, and in other patients, it was completely impossible. It was useless data. Patients were getting better, and then they had an increase in transepidermal water loss. And I remember, I went into the room with the nurses that were doing the measurements, trying to understand, is it operative dependent? What was the issue? And then there was that patient who had significant improvement, and it went up through the roof, and what's going on? And I was looking at the nurse doing it. She was doing well. She was doing it exactly the way it should. And then I looked at the ceiling, and there was an air duct on the ceiling pushing air through the patient and the device. And that was the reason why it didn't work. So learning this, you put patients in special rooms. So all this being said, if we use this in a multi-center trial and we send this to many sites, the chances of having good data is probably low. So closed chamber device is what is currently used in most clinical trials. So the advantage of this is that it's not dependent on ambient air flows. In addition, it's less dependent on pressure on the skin. The way this type of device works is that the top, the condenser, is refrigerated, and it permits the water vapor to turn into ice, and eventually you can do the measure this way. Now, advantages and disadvantages, the closed chamber, as I mentioned, not influenced by air movement, no need to have a room with controlled humidity and temperature. It's easier to use in non-specialized settings. Some people say that it's not, from a physiological point of view, it may be less representative of what happens in the skin. But in clinical trials, I think this is the way to go if one wants to have some reproducible data. Even with this type of device, I've seen trials where this is sent massively to many sites, and the data is not that good. If you don't use sites that are used to do transiputable water loss measurements, sites that really like to do good repetitive work, that have people that are dedicated to do this, the quality is usually lower. So a few tips. So patients need to rest. So obviously we're measuring vapor evaporation. If a patient ran to go to the clinical site, the patient sits down, we do measurements, it doesn't work. So sites need to be able to have patients resting in a stress-free environment. They can't apply the cream in the morning because obviously this has an effect, so this is very important. Anatomical site. So if you do this and you want to see change over time, it has to be done exactly at the same place. So the way we tend to do this when we work at our clinical research unit is we always draw exactly where the measurement was taken when the patient came from baseline, so that when the patient comes back, it's taken exactly at the same place. Pressure also has some effect. Now, a few examples of studies conducted with transiputable water loss. This is a study we published a number of years ago. We worked with Emma Cutman in that study comparing steroids to pimecrolimus to vehicle. So vehicle is in gray, pimecrolimus is in the first blue, and the two steroids are in red and mauve. And what we saw is that we were able to see a decrease in transiputable water loss at day 8 with the two steroids. We saw a little bit of a difference with pimecrolimus. It was not statistically significant. This was a single center study. All patients were seen at our clinical research unit in Montreal. And this paralleled exactly what we saw from a gene expression perspective and a clinical improvement perspective. Another study we published a few years ago, it's a single center study again, looking at the effect of crisaborole on transiputable water loss. So crisaborole is a PDE4 inhibitor with, I would say, what I would call moderate efficacy in atopic dermatitis. And as early as day 8, we were able to see a difference. You can see, what's interesting is that you can see that on the, this was a contralateral study. So one area received vehicle, one area received the crisaborole. You can see nice improvement with vehicle. And for those of you maybe less familiar with atopic dermatitis studies, atopic dermatitis studies with a topical, the placebo quote-unquote response is always high because the vehicles can have a good effect. You partially repair the barrier with a good moisturizer cream. Dupilumab, so this has been presented, it's a poster at this meeting. This first time the data has been presented. This is a 2-center study that was conducted, our center in Montreal and Donald Young in the US. All patients received dupilumab, and we wanted to study the effect on the barrier. It's a complex study with many different evaluations. I'm showing you the transiputable water loss data. So as what has been published previously in the literature, we've seen that transiputable water loss is increased on atopic dermatitis skin. On non-lesional skin of atopic dermatitis patients, it's also increased as compared to healthy volunteers. Over time, when patients receive dupilumab, there's a nice improvement in transiputable water loss. We were mostly interested to see what would happen on the non-lesional skin of patients with atopic dermatitis, hoping that a systemic treatment would be able to improve the barrier. And the results, from my personal opinion, are a bit of a disappointment. So what we saw over time, we can compare that with controls that were recruited at the same time to take care of the possible or potential issue of difference in temperature over time when you recruit patients in a study. They were age and sex matched. So what we found was no significant difference over time. So the change from baseline in this group is not statistically significant. The difference between HV and non-lesional skin of AD patient is a little, if you look at those curves, you can see that that distance is not as big as that distance, but again, it was not statistically significant. So it will be interesting to see with drugs that have more efficacy, maybe with JAK inhibitors, what this would do. Could we, with a systemic drug, have an effect on the barrier on areas where patients don't have active atopic dermatitis, but we know that there's a barrier effect and there's inflammation there. So another way of looking at the barrier is to look at gene expression. This is taken from the study I showed you before, comparing crisaborole to vehicle. This was done in Emma Gutman's lab, so she has a set of genes that are involved in barrier, and what you can see on this slide is improvement. So this is improvement as compared to baseline, and you can see that there was improvement with crisaborole as compared to vehicle in barrier genes. Another example, the study that I showed you before, where we compared pimecrolimus to vehicle to steroids, and again, we're looking at some barrier genes, including loricrin, and what we saw is exactly what parallel transepidermal water loss and parallel the improvement as well. So vehicle, a little bit of a difference when you look at pimecrolimus, but not much, but when you look at the more potent steroids, you do see a significant increase. So another possibility, and I think this is my last slide, is to look at the lipid composition of the skin. This was presented recently at the QuadAI meeting, and it's taken from the dupilumab study that I mentioned before. This was done in Donald Young's lab. So as you know, in the skin of patients with atopic dermatitis, there is a difference in terms of ceramide productions. So some ceramides are increased, some ceramides are decreased. The short chains tend to be increased, and the long tend to be decreased. So this data focuses on one of those short chain ceramides, and what you see over time is that you have a decreased normalization in patients with atopic dermatitis. You kind of don't see much in patients with in healthy volunteers. You might argue that there's a little bit of improvement here, but again, this was not statistically significant. It's another indirect way to look at what's going on in the barrier. And that's my last slide. Thank you. So I promised that we would end on time. So it's 8:24. Any questions? Yes.
Hi, yeah. So I've read about patients having tape strips performed before transepidermal water loss readings. Is that necessary? What are your thoughts on that? Does that introduce extra variable that needs to be controlled?
Good. So tape stripping is a method where we take small tapes, we put on the skin, and then we remove part of the stratum corneum. What's usually done, we've done a lot of tape stripping studies with various sponsors and collaborating with various people, including Emma Gutman. What we tend to use is Q-derms. We tend to do 20 tape strips, so 20 different tape strips at the same area. What happens when you do this is you remove part of the stratum corneum. However, it's very heterogeneous when you look at it from a biopsy perspective, and sometimes you even go as deep as I think the basement membrane, because I've seen a little bit of blood on some patients with atopic dermatitis. Now, this is usually done mostly to look at gene expression or lipids, but it can also be used to look at what happens to transepidermal water loss. In other words, if you want to study what happens in a normal patient, in a normal a patient that would not be challenged, you don't have to do this. This represents more what would happen if you wash, if you have soaps, if you insult the skin. And it has been shown that if you do this, you have an increase in transepidermal water loss. If you compare patients with atopic dermatitis to normal individuals, you see that the slope is much higher in patients with atopic dermatitis. So I think if one wants to have a good, if one devises a study to look at the barrier, I think it's a good thing to add. And specifically in the dupilumab study we performed, this is something that was done. We have not shown the data yet, but it was done. If there are no more questions, I want to thank you all for attending. Thank you for getting up early this morning. 7 a.m. is very early, and I wish you a very nice day. Don't want to take more of your time because I know that there's a late breaking research session that starts in about half an hour. Have a good day. Thank you.